Okay, let's start the session. Our first session is two speakers, the last session, I would say Max Planck Institute family session. And the first speaker is Claudia Felser, Professor, Dr. Director, Frau Felser. Her talk is Kagome lattices, frustration, and topology, or in another order. Please, Claudia.
Topology is everywhere, even in graphene. So therefore, I wait for my talk. Okay, yeah, I'm very happy to be here again. So I was not on the photos because I just came always to the other events in between, but I'm also here since ever. I have the feeling, I feel like I was at one of the first meetings, you know, Tony. Thank you for giving me always the opportunity to come here again. And this time I thought I should be giving a bit more a technical talk. I already know next time I really should talk about chirality because I forgot, I never spoke about chirality here. Anyway, so now I talk about Kagome because this is very strongly related to a few of my people from Bangalore, and I thought I should give credit also to Bangalore. Okay, so I'm very lucky to have very good students from Bangalore, postdocs always, yeah, from always the same group. I don't want to say the name, you know, you will recognize. And yeah, I'm very happy, and they did a good job in Kagome's lattice. So more or less, we know nowadays that topology is not something rare, it's more something common. And the nice thing is we can, using the concept of topology, simply, we can use it to really find new properties, not yet batteries, but we use it for catalysis. Kagome is not the thing, we talk about catalysis, but here for Kagome we are very interested in the magnetic properties, so it's more related to magnetism. But if you see that nearly 30% of all the inorganic materials, and this is more on the metallic and semiconductor side, are topological, so you think it's nothing special. You could even ask, why should we care about topology? But we can simply understand materials with a different viewpoint, and this gives new properties like thermoelectric properties and catalytic properties, quantum properties. People still looking for topological materials for a quantum computer because they think they are stable against noise, so they're surrounding, but so far it's not yet found. But maybe we can find it in the near future. Anyway, so the whole concept is a simple one. I always say this is quite common. So you have two bands in the electronic structure of a material, and you have a band overlap. And this is, if you see the band spaghettis of solids, and I don't have to explain it here, so you have very often overlapping bands. And depending from the symmetry of bands, and everybody, I assume, sitting here who does solid-state chemistry has read the paper from Rolf Hoffmann. So this overlapping band is a common theme in his paper to identify structural distortion. And in topologies also, we look here for overlapping bands, and we know that if we have spin-orbit coupling, so heavy material compounds, then the spin is not a good quantum number, so this is always forbidden overlaps, and we end up with a material which is a semiconductor, which has parts of the conduction band and the valence band and vice versa, and we have the very nice surface states in this connecting now the valence band and the conduction band, and they are super stable. And what I really like is that we have here surface states where the spin and the momentum is locked. So these electrons are chiral, so I hope I can use this chiral electrons for chemistry. But there are also other possibilities. So depending from the symmetry, the crystal structure of the material, we can have these crossing points in the electronic structure. And if we have no central symmetry, so we could have these crossing points where the electrons in the bulk are chiral, so we have these Y points in the bulk band structure, which are chiral, so they are like magnetic monopoles, which act as source and sink, and they have very interesting surface states. So therefore, people look for a long time already now for these crossing points, and especially for the crossing points if we have no central symmetry, because then we have these Y points. Otherwise, we have the crossing, like in graphene. But it's a Dirac point, so there is not this Y physics at place where you have this chirality of the electrons in the Y. So now, the nice thing is if we go to magnetic systems, so because we break time reversal symmetry, all these crossings are Y crossings. So they all have this very nice Berry curvature, and they have the corresponding properties, which you will learn a little bit. So crossing in a magnetic compound is always related to Y points, nearly always. And if we even have a magnetic material, we could design the ideal Y material, which has only 2 points, which is the case for one magnetic material like europium, cadmium 2, arsenic 2. Also, Superjit worked on this, but I don't talk about this. While in materials where you have these crossing points in materials which have no inversion symmetry, they come always in 2 pairs, so you have always 4 Y points. So this is one starting point, and this is known since some time, and I already talked about this 2 years ago. But now we also know that from all the magnetic materials, we have even more topology is more common. So we have to characterize now not only the 230 space groups, we have to have 1,651 magnetic space groups. And so we have an infinitive number, more or less, of magnetic materials which are not yet discovered with the corresponding interesting properties. And here, so I had this night I couldn't sleep so well. Here we assume still that the magnetic moments are sitting on the atom position. But I think this is an assumption which is wrong, because very often the magnetic moment is even modulated, and it's not sitting on the atomic position. So we still have a lot to do. We can come up with even going beyond 1,651 space groups by assuming that there's a disentanglement between moments and structure. Okay, anyway, so this is also from our review from 2022. So there are many interesting properties which you can find if you investigate all these topological materials. Some are even related to energy conversion, so like the Anomalous Nernst effect, which I like very much. So this is much larger in this magnetic system, which show topological properties, and it goes really with the topological properties. But you see also fundamental new physics. I have not the time to explain this because this is a short talk. So it's a so-called chiral anomaly, and these are more or less quantum field theory, interesting theory, which here the chiral anomaly would explain the asymmetry between matter and antimatter, which is not shown in high energy physics, but where we could eventually see that this Dirac equation solution is right. But we also can see very nice quantum effect like quantum anomalous Hall effect or the axion electrodynamics. So quantum effects from energy conversion, quantum effects, and some tabletop experiments for high energy physics. And I think the light-matter interaction is something which is still to explore. So this is a paper was published in 2020 where we identified the antiferromagnetic topological materials, and more or less we still live on this kind of material. So if you see these groups of materials, they are very familiar to you because they are only the antiferromagnets where we know the crystal structure and the magnetic structure. And the reason is that you know the magnetic structure we learned also today already. So you need neutrons, and they are very difficult then to investigate because you need very big single crystals and so on. Therefore, there are not so many, and there are only really good crystal structure and magnetic structure for materials which are already known because of their interesting physics. And I will talk about a few groups of them today, which all have a common motive: the Kagome lattice. So what is a Kagome lattice? So the Kagome lattice is a structural arrangement of the atoms which are in triangles, and they are in this very nice, beautiful triangular arrangement, and sometimes you can even see it in some equipment in your household and so on. And what is here the problem? So if we have an antiferromagnetic arrangement, if you want to arrange the spins on such a Kagome lattice, and therefore this is already famous in some time. So if you have one spin up and one spin down, you don't know what you should do with the third corner. So it for sure has magnetic frustration. So this is a big question, and people think there is even fractional charge related to this, and maybe the fractional quantum Hall effect and some interesting, super interesting quantum physics with this. So therefore, this field is interesting, and people are always looking for new materials in this family of materials. And people who know me, I like a big class of materials, which are the so-called Häusler compounds. They have the composition X2YZ. So they are simple qubit materials, and they exist as antiferromagnets. They are quite honestly boring if they are cubic and antiferromagnetic. But we can have structural distortion in this material, and if you distort the material along the 1-1-1 direction, you end up with a Kagome lattice. So this means here we have a class of material where we have thousands of members, and very often we have in the phase diagram hexagonal and heterogonal distortion depending from the synthesis condition. So we can make this compound to, you see here the triangles. So you have two Kagome lattices quite close to each other, so it's quite three-dimensional structure. And so what we did, so this is one example, manganese-3 germanium or manganese-3 tin. So when we recognize that we have Kagome structure here and potential frustration, and this compound is antiferromagnetic, when it's in the hexagonal structure, we were thinking, what could be the magnetic structure? So we calculated at this time with Jürgen Kübler, and he's now 86, still one of my best co-workers, all the potential frustrated lattices in this material, but we checked also about the energy of the corresponding ferromagnet, and here the simple antiferromagnet when they are out of plane magnetized, and here are all the possibilities which are allowed, allow a spin frustration in plane. So this was already in 2012, so we were interested, but at this time we didn't see the impact of this material itself, because the Kagome lattice is now so popular, because if you simply make a tight binding model, for example, simply you put hydrogen atom on this Kagome lattice and you would calculate the electronic structure, it's nearly as interesting as graphene, maybe even more interesting, because the electronic structure would lead to a flat band, a Van Hove singularity, and a Dirac cone. So this is very interesting. People who worked on superconductivity, like me, I belong to the older generations, they know Van Hove singularities are also appearing in high TCs at the Fermi energy, the energy which separate occupied and unoccupied states, and they are connected always with electron nesting. So we have charge density wave instabilities, spin density wave instabilities, and superconductivities, like in the high TCs, connected very often with this Van Hove singularity. And so here you get a fingerprint simply where you have topology, superconductivity, and charge density wave instability, and this flat bands, which could lead to Kondo physics, whatever. This makes this compound so interesting. So this leads to features in the density of states, which are this very high peaks in the electronic structure for the Van Hove singularity, and for sure a very big peak for the flat band. And some people also think so flat bands leads also to superconductivity. So this is a three-dimensional sketch. You see here the flat band, and you see here the Van Hove singularity. One part of the band goes up and one part of the band goes down, and you see here the Dirac cone, similar like what we know for graphene. And if we apply spin-orbit coupling or magnetism, so this crossing point, we can open a gap here, which leads then to very interesting surface state, as we already know, and non-trivial topology in this material. So we have now, if we go to materials which have this Kagome lattice possibility to see frustrated magnetism, correlation, superconductivity, charge density wave, and topology. It's like you can do everything. So can we understand these materials and use design schemes to get interesting properties out? So from topology, we know if we have this crossing point in the electronic structure, this y point, so we can calculate the Berry curvature for this, which is simply a geometric phase. I always say in topology we do nothing else than we paint the bands which we have with colors of the Berry curvature, and simply we see totally new physics, because the bands which were before black, they are now red and blue, and we get very nice, interesting properties. Because, oh sorry, now I have to go back, I hope. Oh, now I have to find out how to go back. So red, but yeah, okay, yeah, good, thank you. So this leads to interesting properties. For example, the anomalous Hall effect in this material. So this is an additional contribution to the Hall effect in magnetic material. Is very large in this material, and there is a large anomalous Nernst effect, and the Nernst effect is exactly what I want to have, large Nernst effect for energy conversion, to take wasted heat into electricity. So now we can, and before topology, people simply thought that the anomalous Hall effect goes simply with a magnetic moment. So I have zero magnetic moment, like an antiferromagnet has no net magnetic moment. I have no anomalous Hall conductivity. I have no Nernst effect. So this was until 2013. If I have a big moment, I have a big anomalous Hall effect and a big Nernst effect. But then people like Naragoza already developed the theory, and they recognize that certain features in the electronic structure, like crossing points, for example, can lead to an enhancement of the anomalous Hall conductivity and the anomalous Nernst effect. So now, how can we find interesting material? And indeed, at this time, when we looked for the frustrated magnetism in the antiferromagnetic manganese-3 germanium and manganese-3 tin, again with Jürgen Kübler, so we found out that even these are antiferromagnets and they have no net magnetic moment, they had a giant Hall effect, a giant Berry phase. So we thought something is wrong, you know. We went to Stuart and he said, no, something is wrong. No antiferromagnet, no anomalous Hall effect. This must be a mistake of the code or whatever. Anyway, at the same time, Alan MacDonald came up with a similar crazy idea in another system, manganese-3 iridium. So we were encouraged to publish this without Stuart and without Binhai, because they didn't believe the results. And Ajay and Nayak, so he made this compound in my group, and he measured the anomalous Hall effect, and indeed he found an anomalous Hall effect. And this is a Hall measurement simply, and you see here a large jump, and this is unexpected for an antiferromagnet. So you would expect here simply a linear line, which you find for the Alan MacDonald compound, but not for our compound. And at the same time, Nagajuchi, he investigated manganese-3 tin, so he found the same, so it was clear it's not an impurity and it's not a mistake. Nowadays, we know that we can find in this topological antiferromagnets behavior, like in ferromagnets, unusual behavior. And then you can also look for this compound for the Nernst effect. Okay, so now this has inspired more groups to work on Kagome lattice in this metallic system, especially also the group of Joe Shekelski and the MIT group. They used mainly iron compound. They even changed the composition to go more for three-dimensional material, like our manganese-3 germanium, to two-dimensional materials, and he found Dirac fermions in this ferromagnetic Kagome lattice, so there is now much more activity, especially because of this interesting electronic structure. We looked for a ferromagnet here because I also have applications sometimes in mind, like Chirality. You know, I like quantum materials, but there should be something useful coming out. So because this is, for example, a cobalt compound with a Kagome lattice where the spins are out of plane. So if you have this anisotropic compound and the spins are out of plane, so this leads to hard magnetic behavior. And this means in a zero magnetic field, I see still this interesting quantum effect. So we made this compound, the single crystal, and we showed the chiral anomaly in this paper. This was simply the editor wanted to see the chiral anomaly because everybody is excited about this high energy physics properties, but it has no impact at the end of the day, but it shows so that depending from where we measure our magnetic field relative to the current, we see a positive magnetoresistance effect or negative, which shows evidence that we have this Y physics. But we saw also in photo emission experiment really that we have this linear dispersion here, so it's a little bit above the Fermi energy in the virgin compound as predicted by the calculation, but we had to put some potassium on it and we saw the crossing. Anyway, we saw also the predicted surface state in this compound, everything was fine, and we got 2 papers and 2 Science. This was good. But what is more interesting is we saw here also a very nice anomalous Hall effect, which exists even at 0 magnetic field. The value here, the anomalous Hall conductivity, and it exists also in 0 field because we have this magnetization perpendicular. And for the expert here, so to Kura and Nagaosa, they have this very nice characterization of the anomalous Hall effect, where we can prove nowadays whether it's mainly intrinsically by topological properties driven, and this is indeed the case here in this material. But the nice thing is also that we thought, so we are interested in thermoelectric materials like Viva's group, where all my people are coming who are working in this field. But in thermoelectric materials, you always need semiconductors which are N and P type, so it's very complex. You must make very complicated devices, and you have a lot of contacts where you can have leaking current and all these other problems. So the Nernst effect is a much easier device because you simply take your solid and you make 2 contacts, and you have a temperature gradient, and then you can measure the Nernst. And indeed, so this material shows giant Nernst effect, unexpectedly high for this material. So this is more or less a recipe using these crossing points around the Fermi energy to design more Nernst effects to have magnetic material with high energy conversion efficiency. So this is now Satya, did his PhD, I think, in Bangalore, and joined my group. He's now back. He got an ITT position, right? Position in India. Anyway, so the other thing is you see also in this material very interesting quantum effect. So if you simply do STM here at the edges of the cobalt 3 tin 2 sulfide 2, you see if you do STM, so you apply a bias, voltage bias, you see nice edge states which are quantized. And if we simply look into detail in this material and measure the conductivity per layer, per magnetic layer, so we see really something like, if you see here this curve, you see something like it's quasi-quantized per layer. So this is an idea that we think in this magnetic material, sometimes if they show exactly the property, you see probably a 3D quantum Hall effect, which is quantized per layer in this material. So more or less, we thought, okay, this is already good. We have one material where we could tax the chiral anomaly, the anomalous Nernst, the anomalous Hall, and the quantum anomalous Hall effect, and here the photo emission and the APIS data. So can we now think can we design other materials? So we went back to very simple material and worked here also with Andrei Bernavik to iron germanium, a 1,1 compound, and we simply looked, can we see the fingerprint? So every theoretician liked to do models with s electrons, but reality is more complex. So in a magnetic material, you have d and p electrons. And indeed, we find, if you see very nicely as well in the tight binding model as in the real band structure, always the same fingerprint. And look like that the electronic structure is only made by flat bands, Van Hove singularities, and crossing points. So it's like there should be a lot of interesting physics in this compound, which was not seen before, okay? So here we even have this interesting physics at the Fermi energy. So then we thought, okay, there are big groups of material which are structurally related, for example, to iron germanium. You see the iron germanium structure with the iron, here are the triangles, the iron triangles, which builds the Kagome lattice. So there are many other compounds which have the composition. Oh, this is a 6, sorry, this is a mistake. So it's magnesium, iron 6, germanium 6. So we simply double the unit cell and fill into some voids some magnesium. And then we can make all those compounds with vanadium, chromium, manganese, iron, cobalt, nickel. and gallium, germanium, indium, tin. Now you can calculate the probability that you can make such a new Kagome lattice. You know, I like Häusler compound, and here I have a new toolbox with, like the perovskites, with thousands of compounds, you know, which allow me to tune the electron count to the number of electrons I wish. Okay, and like in the iron germanium, also the magnesium germanium, iron germanium, the 166 compound, has the same fingerprint. They consist all of this interesting crossing points, Van Hofe singularity, etc. Okay, so now it only doubles the unit cell. Therefore, we have here 2 bands, for example, two Van Hofe singularity and crossing points here at the same time. So now you can say, okay, you did a lot, now interesting, but you have again a pool of compounds. What is interesting with them? So Subhajit, for example, he came from Bangalore. He's still interesting in finding record values of Nernst effect. So he investigated yttrium manganese 6 tin 6 because he saw that this is probably a good compound. And indeed, now you see here are ferromagnets and here are antiferromagnets. These are common ferromagnets, and these are the values which people thought are the values which you expect in magnets for Nernst effect. And now you see that all these topological materials are much higher in their Nernst effect, even the antiferromagnets, which people believed had no anomalous Nernst effect. So in this sense, these are all nice materials which we should systematically investigate for getting really high efficiency in energy conversion in magnetic materials using topology, simply looking for crossing points at the Fermi energy. The other thing is, many of them, really, if you look more carefully into it, you see they really show strange behavior in the transport properties, like here in the resistance, for example, there are jumps. And these jumps are indeed, and we even can, they show nice quantum oscillations, so we can make very nice single crystals. So I'm now really amazed that we even can grow single crystals of ultra high quality in magnetic compounds. This is not magnetic compound, but still. So where you have very nice quantum oscillations, so that you get from the measurement the whole band structure, and that you really can revisit all this compound, and you see even some interesting transition, and indeed expected, what we have expected for a system which has a Van Hofe singularity. This compound shows a Van Hofe singularity, and related to the Van Hofe singularity, they show, and the flat band, they show a phonon softening, they show charge density wave. So this is also predictable by theory. So here we calculate the phonon frequency, and if you find values below 0, you already see, and if you look at the symmetry of the phonon, you can already predict where the structural distortion is and where the charge density wave appears. So here you see, for example, we find the charge density wave between the layers, so between the tin atom, and this was then verified by experiment. So now we did it for all these A elements, and manganese, germanium, 166, manganese tin, manganese, germanium, blah, 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 blah. And there are few compounds known as antiferromagnet. There are few compounds not known. There are few compounds having a structural distortion. And indeed, we could identify 3 types of charge density wave instabilities in Kagome lattice. So it shows already that in this 166 compound, which has 1,000 members, we can have different charge density or different instabilities. Now I'm too fast again. Takes some time. Okay, so different instabilities. Different instabilities. One, which is very interesting because I like chirality. For other purposes, like catalysis, for example, you can make these materials which have a chiral charge density wave if they have the minimum here at the A point, and then you can have the charge density wave which you already saw in scandium, vanadium, tin, and you can have a third type of charge density waves. So many of the materials are not yet investigated, so we have now, unfortunately, Subhajit also got a job in India at a NISA, so after 3 years and Humboldt, so I again have to find somebody, so you know, I'm waiting, who continues this synthesis. Because now you can say you combine all this transition metal main groups with all these compositions of alkaline earths and rare earths and so on. So you have many possibilities. And all the red ones show they are unstable at low and high temperature, and the blue ones are all where we expect a certain charge density wave and electronic instability, and eventually superconductivity. So Subhashit, as a farewell present, he gave me another system which has, so it's not only the 1,1 composition and the 1,6,6 composition. I think this family is infinitive. Okay, I would say he said, okay, why not looking for some distorted Kagome lattice? And indeed, also here you can see a large anomalous Nernst effect, anomalous Hall effect, etc. So which means, so despite of the ordered Kagome, so if they have a slight distortion, and this is quite common because they have this electronic instability because of all this Van Hove singularities, inflation of flat bands and Dirac cones and Weil cones, it's quite common. So here you have Weil cones and also very giant anomalous Hall effect. So it's really interesting because we have here with the Kagome family very nice interplays, and there's another family which is even interesting from other people, especially in UC Santa Barbara, and Tony, I think, is aware about the 1, 3, 5 compounds. It's again, it has not so many members with the, like the 1,6,6 compounds, but it shows superconductivity already, and it shows charge density wave instabilities, and it shows even some anomalous Hall effect in the same compound, in the cesium, in the vanadium compound. So they are also extremely interesting because also people think if we have a chiral charge density wave symmetry is very low, a chiral symmetry and superconductivity, we might have topological superconductivity, and it might be interesting for Majorana fermions or some interesting topological quantum computing. So we liked especially this compound because I liked chirality, because it turned out that in this compound, and this was work we did with Philip Moll, so if we apply a magnetic field, depending whether we apply it perpendicular or in direction of the current, we get a chiral current. So we did second order transport measurement. So magnetoelectric effect, which you normally only see in chiral organic crystals, for example, or in tellurium, we saw a nice large effect under a magnetic field, I have to say, in this compound, which I like, because I like, so as a chemist, if I want to do chiral catalysis, if I have a material I can switch from one chirality to the other chirality, this is super cool. Okay, this is for the organic. So this would be a part of my my chiral talk. Anyway, so here we see simply, sorry, again, so however, the chirality in this system is not there if we don't have a magnetic field. So you see it's flat here. And indeed, also people who have hoped that this is a chiral superconductor were disappointed because we had a collaboration with Aaron Kapitolnik to do Kerr effect to measure whether time reversal symmetry is broken in this compound. And despite of muon investigation, which said time reversal symmetry is broken in this compound, it's not the case. From this, you really need a magnetic field, and this is indeed what we also did in an investigation. Sorry, the slide is not so nice, with Philip. So if you, in this cesium vanadium 3 antimony, if you have a pristine compound and no magnetic field, you don't see the chiral current here. But if you strain it or apply magnetic field, you see the chiral current here. So you need some external forces. So the superconductivity appears without strain and without field. So it's disconnected from the superconductivity. Anyway, so this is only the beginning of the search for flat bands, so people now getting crazy about flat bands. There are also the pyrochlore lattice and the Lieb lattice, which allows for flat bands, and we did some systematic investigation to look for flat bands, because Andre thinks he finds a room temperature superconductor there. I don't think so, because I'm a chemist. Flat bands makes everything dead. You need some dispersion, and but it's really a nice playing ground, I think, for seeing interesting properties in this material. I hope I gave you a little bit the impression. so that you can find a lot of interesting stuff there. And since there are like 999 at least unexplored compounds where German solid-state chemists made the compound but never measured even the transport properties, they probably didn't find anything like charge density wave instabilities, etc. There's still a lot to do and interesting stuff to find in these compounds. And with this, I thank you for your attention, and I thank my group for helping me, and Santi is a new collaborator from Spain who can do this investigation of electronic instabilities in this material, and I think I have my old co-workers on the theory side, and I'm open to answer questions. Thank you. And I stayed in time.
Thank you very much for your interesting talk and for being on time. We have now time for questions. Please don't hesitate to ask questions. Okay, while you're thinking, let me ask you a question. It's
this is a tough question.
Responsibility of a chairman to fill the pause while people thinking. So one of the appeals of topological materials is topological protection, which allows long-term transport. In case of magnetic materials, unlike graphene, it's spin. How long in your experiments or for your compounds you see topologically protected spin transport? Is it microns, tenths microns, I don't believe in millimeters.
Yeah, but we already had some discussion here, and indeed we find it even in a magnetic material now. Anyway, so we find ultra-high mobilities in these materials, and we find in the chiral materials really non-magnetic one-spin polarization, even in photoemission. Okay, we can investigate that, and we do some catalysis, which needs also, and like in tungsten diphosphide, we had like a millimeter, like similar like in graphene. And now we have even a magnetic material where we see this ultra high mobility, which is related. Anyway, we have to do more transport property experiments. And for this, we have Uri Woll now in our department, which does NV Center, to look for the flow of electrons.
Currently, it's local topological protection, not transport over long distances.
No, it's transport over long distances. But what we measure is simply that we have ultra-high mobility in this material, okay? And we see this deviation from Wiedemann-Franz law and all the things which is seen in graphene, okay. You know? This hydrodynamic flow, and we did some work with Ami Yacobi on the hydrodynamic flow in tungsten telluride 2. But now we have even a magnetic system, which I think is even more exciting, because normally we didn't see really quantum oscillation, really good mobilities in magnetic system. Nobody saw before, but we see this in this Kagome lattice. Okay.
Okay. Other questions? Okay, Tony, please.
Thank you, Claudia, for an exciting talk. You were talking about the magnetic space groups and how they don't accommodate sort of periodic waves of magnetism and so on. So is there a relationship between the four-dimensional space groups that you get in commensurate crystal structures? And
it's a very good question. This is probably the way to go. And maybe because we want to understand how real space is influenced by reciprocal space, okay? But if we sit on the atoms, you know, like what you say, there might be the going to higher dimension might be the way to go, also to look for topology in magnetic system and even in charge density systems, no? But he has done the topological characterization of charge density or misfits. You're right. It's a very good idea. I just dreamed this night, and I didn't have a solution, but you're right. You have to do it. Treat it like quasi-crystals or charge density waves. You're right.
Yeah,
also from the theory, you can simply adapt then the theory in higher dimension. Very good. Thank you. We have to make you a course. Happy to the theory.
And I've got a much more prosaic question. With all these, I think you said there are thousands of Heusling compounds.
Yeah.
So Are any of them used commercially for any applications at the moment?
So I think I don't know what exactly is going on the spintronic side, because we sold some patents to some companies and they did something on Häusler compounds, and Stuart is working with Samsung, but he doesn't tell me, even in the night, accidentally. Anyway, but there are other applications. Häuslers are also in application nowadays for thermoelectric. Okay, so the SETI is still 1.5, but we already have ideas how to improve it, you know, even because the magnetic field is fully ignored to go maybe, and the SETI of 3, which is already achieved in some compounds, but only in certain circumstances, would be compatible with oil. And this is what we want to have, energy efficiency. So I think maybe with new creative ideas, I think one maybe is like batteries, but they are already in commercial. But I think thermoelectrics is application, but not the big application you want to have. It's more niche application for certain application, and for magnetism also. And I think they're also an application for neutron scattering, capturing neutrons and stuff like this. So several.
Thank you.